Hey everyone, welcome back to another LeetCode problem solving video. Today we are cracking LeetCode 441, arranging coins. The problem gives us a total of n coins and our goal is to build a staircase where the first row has exactly one coin, the second row has two coins and the third row has three coins and so on. The catch is that the last row might not have enough coins to be fully complete. Our job is to return the total number of complete rows we can build. While you could easily simulate this row by row, doing so would be too slow for large numbers. Today, we are going to use an incredibly efficient binary search approach that finds the answer in a logarithmic time. Let's look at our strategy first and then we will jump straight into the code. Before looking at the code, let's understand the simple math that powers this problem. If we manage to complete exactly k rows, the total number of coins used follows the standard arithmetic sum formula k into k plus 1 divided by 2. Instead of guessing row by row from 1 upwards, we know our answer must lie somewhere between 0 rows and n rows. Because this search space is perfectly sorted, it screams binary search. Our approach works like this. We establish our boundaries, a left pointer at 0 and a right pointer at n. In each step, we check the middle row well made and calculate how many coins it would take to build a complete staircase up to that row using our formula. If the calculated coins match n exactly, we have found our perfect match and return made. If the coins are less than n, it means we still have leftover coins and can try to build more rows, so move our left pointer up. If the coins are greater than n, we overshoot our budget, so we move our right pointer down. When the search space closes, our right pointer will naturally sit on the maximum number of complete rows possible. Let's see how this translates into C++ code block by block. So to begin, we declare our function arrangeCoins, which takes an integer n. We initialize two 64-bit pointers, left set to 0, right set to n. We use long here to prevent any potential integer overflow when multiplying large row numbers later on. Right after we start our while loop, which runs as long as left is less than or equal to right. So let's do that. So long left equals to 0, comma, right equals to n. Now while left is less than equals to right. Sorry, okay, less than equals to right. Now inside the loop, we calculate our midpoint mid safely to avoid overflow. Immediately after, we use our mathematical formula made into mid plus 1 divided by 2 to compute the total number of points required to build a staircase up to that mid row level. So let's do that. So long mid equals to left plus right minus left divided by 2 and then long coins equals to mid into mid plus 1 divided by 2. Now we perform our binary search checks. If the calculated coins are exactly equal to n, we hit the perfect jackpot. We have used every single coin to form complete rows. So we immediately return mid. So let's do that. If coins equal and then return mid. Now if the calculated coins are strictly less than n, it means we have still have a surplus of coins left over. We can definitely afford to build more rows, so we shift our search to the upper half by moving left to mid plus 1. So else if coins less than n, then left equals to mid plus 1. Now if neither condition is met, it means coins is greater than n. We ran out of coins and built too far. We narrow our search to the lower half by moving right to mid minus 1. If our loop terminates without hitting an exact match, the maximum possible number of complete rows will be resting inside the right pointer. So we simply return right. So else right equals to mid minus 1 and then return right. Now let's first of all run and check whether it is passing the base test cases or if there are any syntax errors. Sorry, let's wait for a few seconds. Now let's run it. Now also submit to check whether all test cases are getting passed. Okay, every test cases is getting passed. Now let's quickly try run it. So let the input n equals to 0. So left equals to 0, right equals, sorry, input n equals to 8. So left equals to 0, right equals to 8. Now loop enters. Mid equals to 0 plus 8 minus 0 by 2, which is equals to 4. We calculate coins needed for 4 rows. Coins equals to 4 into 4 plus 1 divided by 2, that is equals to 10. We compare. Is 10 equal 8? No. Is 10 less than 8? No. Since our 10 is greater than 8, we hit our else block. Right becomes mid minus 1, which is 3. Now left equals to 0, right equals to 3. Loop enters. Mid equals to 0 plus 3 minus 0 by 2 equals 1. Calculate coins for one row. Coins equals to 1 into 1 plus 1 divided by 2, which is equals to 1. Now compare. Is 1 less than 8? Yes. We can build more rows. Left becomes mid plus 1, which is 2. Now left equals to 2, right equals to 3. Loop enters. Mid equals to 2 plus 3 minus 2 divide by 2, which is equals to again 2. Calculate coins for 2 rows. Coins equals to 2 into 2 plus 1 divided by 2, which is equals to 3. Compare, is 3 less than 8? Yes. We still have extra coins. Left becomes mid plus 1, which is 3. Now left equals to 3, right equals to 3. Pointers mid loop enters one last time. Mid equals 3 plus 3 minus 3 divided by 2 equals to 3. Calculate coins for 3 rows. Coins equals to 3 into 3 plus 1 divided by 2 equals to 6. Compare. Is 6 less than 8? Yes. Left becomes mid plus 1, which is 4. Now left is 4 and right is 3. The loop condition left less than equals to right breaks. The function executes return right, which evaluates to 3. Looking back, 3 complete rows take 6 coins, leaving 2 coins left over, which isn't enough to complete a fourth row. Our answer is 3. which is 100% correct. Now let's quickly discuss about the time complexity and space complexity. So the time complexity, because we divide our search range completely in half with every single iteration, the search space reduces exponentially. This gives us a highly optimal logarithmic time complexity of order of log n. This is incredibly fast compared to the linear simulation approach. And the space complexity, now take a look at the variables we allocated. We only created three primitive long log integers left, right, and mid to manage our search boundaries. No auxiliary vectors or data structure are used, giving us a perfect constant space complexity of order of 1. And that is how you solve the arranging coins problem using binary search. Finding a sorted mathematical relationships with a search space is a great way to optimize linear loops down to logarithmic runtime. And if this block by block breakdown and visual dry run help the logic click for you, make sure to slam that like button, subscribe to the channel for more clean LeetCode walkthroughs, and let me know if you have any kind of doubt in the comment in this problem in the comment section. Keep grinding those problems. I will see you in the next video.